So in this third section I'm going to discuss problems in general relativity. You'll notice a little star there, and this section has a lot more technical details, and so here I'm just going to try to give a little bit of a flavour. Let me just put it into some context. In general relativity, the background mathematical structure is a differentiable manifold, four-dimensional differentiable manifold with a Lorentz structure, which gives you the causal structure of the manifold. And the Einstein field equations constitute a set of differential equations that govern the fields, the metric and any matter fields, and they constitute a hyperbolic system of quasi-linear partial differential equations. Of particular interest, and this is normally done in the vacuum case when there's no matter, is the so-called Cauchy problem and setting up a well-posed initial data problem. Within this context, once you've set it up as a rigorous mathematical problem, you can actually pose and attempt to answer various types of mathematical questions. Now, as I said, I'm not going to try to go into too much detail. There are a number of problems that arise. Some of them are differential geometry problems in the sense that the Einstein field equations are generally covariant, independent of coordinate choices, which raises some issues. There are problems trying to prove the existence of solutions, existence and uniqueness, and there are problems trying to generalize the theorems to situations which have lower differentiability, which would be of interest in physics. There are physical problems that would not necessarily be smooth. The geometry would be necessarily smooth. Perhaps the most famous theorem in GR, which I'll just state as a theorem, so this is not an open problem, although many open problems still arise from this. So the singularity theorem is perhaps the most important theorem, possibly even within mathematical physics itself. Penrose was the first person to talk about singularity theorems and prove a theorem. Hawking later applied the mathematical results of Penrose to situations in cosmology, and the book by Hawking and Penrose perhaps summarizes the status of the singularity theorems best. We can see here a relatively technical definition, statement of the theorem, but basically it says that generically solutions of Einstein's equations, namely spacetimes that arise as solutions of Einstein's equations, have singularities. This theorem has been proven since in various cases, which has led to many more open problems. But let me just move on to perhaps the one that's of most interest now, the so-called cosmic censorship hypothesis. So the general theorem of Hawking and Penrose implies the existence of a singularity, but doesn't say anything about its nature. The first solution to be found that had a singularity was Schwarzschild solution, but in the case of the Schwarzschild solution, there exists an event horizon which shields the outside of the horizon, namely us, from the singularity within. So it's not a particularly damaging singularity. So the question is in general, are the singularities of the type of Schwarzschild and therefore relatively meek, or are they more dangerous? And in order to study this, Penrose proposed the so-called cosmic censorship hypothesis. Whoops, which basically asks the question, is the Schwarzschild situation where an event horizon develops the generic situation, or is it not the generic situation? How serious are these singularities going to be? Now, of course, this question has to be framed in a rigorous mathematical fashion. Let me see, where am I? We need to have a particularly well formulated expression of this censorship to be able to answer a question, and that's one of the problems. There is no well-defined formulation of of this particular hypothesis. So people try to prove sub-cases, if you will. One of the problems that arises is that there are known solutions of general relativity in which there are no singularities, or in which there is a singularity but it's not enveloped by a horizon, event horizon. So the problem is you can't prove a result that says there are no singularities that are not shielded by an horizon, because there are known examples. So we have to prove a theorem that says in general there are no destructive examples, which makes the conjecture harder to prove. There are actually two different versions of this conjecture, related to each other but distinct. The first one prove that for a general initial data, generic initial data, using the evolution equations of GR to propagate the solution, there cannot develop any naked singularities. Now, this is a well-posed problem, but still not solved, although it's been studied in some particular subcases. You can see here I've stated the problem. Prove the weak cosmic censorship. The second one's more technical, and here is it stated, but both aspects are to do with the fact that general singularities in general relativity that develop from well-posed data have event horizons. Now there are a number of other problems that are of interest, which I'll just skip through here. These are conjectures that would, if solved, would give us some opportunities or lead to possible roads for proving the cosmic censorship hypothesis. Another class of problems in GR, mathematical problems, is talking about stability of solutions. Famous solutions like the Schwarzschild black hole or the Kerr black hole, which is a rotating black hole solution. Are these solutions stable? Are they stable to certain types of perturbations? There's also the question of uniqueness. Given a certain situation, is the only solution a black hole, and is the solution, if it is a black hole, one of the classical black hole solutions like Schwarzschild or Kerr? So stability and uniqueness, of course, within the theory of differential equations, since we have a well-posed problem, these are questions that we can ask. Unfortunately, they're very difficult to answer. There is some progress in the case of Schwarzschild, but the Kerr-Newman, the Newman is the generalization of the Kerr solution. The Kerr-Newman has not yet been proven to be stable, and this is an area of intense research currently being undertaken within both general relativity and analysis in general. There are also problems that have a more cosmological origin, which I'll talk about in another section. Various other problems, the role of scalar curvature invariance. This is something that I'm interested in myself, trying to describe the geometry in terms of scalar invariance as opposed to tensors. And I'm going to stop there.